Folks, in this video we're talking about heats of formation and reaction enthalpy, making stuff. So let's get going. We have three objectives. I want you to be able to define heat of formation. I want you to be able to define reaction enthalpy, and I want you to be able to use heats of formation to calculate reaction enthalpy. Neat, let's get going. So heat of formation. Well, this is the heat or thermal energy that's either going to be released or absorbed when 1 mole of a compound is formed from pure elements. So we'll look at some examples. The heat of formation, the symbol we use for this is delta H F, delta H being our heat guy and F being for formation. So this can be a positive value or a negative value. If it's a negative value, that means it's exothermic and that we are releasing heat during the reaction. If it's positive, that means heat is absorbed during the reaction. And so the units on delta H are usually kilojoules per mole, generally speaking. And usually when delta H's are measured at 1 atmosphere of pressure and 25 degrees Celsius as the temperature. And so these values only really apply when these conditions are met. So the heat of formation for pure elements in their usual state of matter is always going to be 0. So if you see hydrogen gas, which likes to be H2, because hydrogen gets lonely, or if you see nitrogen gas, that's the state that these elements are found in at 1 atmosphere of pressure and 25 degrees Celsius. Mercury, generally a liquid at 1 atmosphere and 25 degrees Celsius. Iron, usually a solid. So these puppies would all have delta H's of formation of 0. And so these values you can usually look up in a table. I would never memorize these, ever. So let's look at some examples. Here's a nice reaction. This shows hydrogen gas and oxygen gas coming together to form water. Well, delta H for liquid water, this number, negative 285.8 kilojoules per mole. That tells me that every time 1 mole of liquid water is formed, 285.8 kilojoules of energy is released. Neat. That's how much energy is given off when a mole of water is formed. Liquid water, to be precise. It's different for gaseous or solid water. Here's another example. If we take carbon and oxygen and combine those to make CO2, well, we can find delta H for CO2. That's going to be negative 393.5 kilojoules per mole. So every time we make 1 mole of gaseous CO2, we're going to release 393.5 kilojoules of heat. Neato. So here's a table with some delta H values in it. This is pretty typical looking, where you have some names, a formula, and these delta H values listed in kilojoules per mole. And you can see that generally they're going to be negative values. Occasionally we do see some positive values in the mix, but for the most part these dudes are negative. All right, neat. Just wanted to show you that. So let's talk about enthalpy, reaction enthalpy. We can also call this enthalpy of reaction, or even heat of reaction. A few different names that can go on this. Well, that's similar to formation. It's going to be the heat absorbed or released during a reaction, not just when a single compound is formed. And it can also describe a phase change, when things change their state of matter. Whenever chemicals react or change states of matter, energy is going to be either absorbed or released during that process. So we call this the delta H of the reaction, telling us how energy, specifically heat, is released or absorbed during a process. So there's a few different ways we can measure this. We can use a calorimeter and take measurements and do calculations and actually run these experiments. We can do this cool thing called Hess's law, which we're not going to talk about now. Or we can use delta H values to for the product and reactants to calculate the delta H of reaction. So let's talk about how we're going to do that. So for starters, we're going to figure out the delta H of formation for everything that's formed during the reaction, and we're going to add up all those numbers. Products are the things that are formed during a reaction, my dude. So it makes sense that if we're looking at the heat of formation, we would add up the values for things that are formed. Okay, and we're going to subtract from this heat of formation for everything that is destroyed, because like destroyed is the opposite of formed. So if something is destroyed, we're going to take away that heat of formation. We added up the heat of formation for things that were formed. We subtract for things that are destroyed. And during a reaction, well, the reactants are destroyed and they're destroyed to make those products, my dude. So we do need to account for the coefficients in our balanced chemical equations. Well, let's do a little practice with that. I want you to calculate the delta H of this reaction using the table over here. So I don't know, why don't you pause the video and see if you can tackle that, see if you come up with the correct answer. It's not too difficult. Sweet. Well, maybe you paused and tried it. Hopefully you did. Let's talk about it together. First thing I'm going to do here is say, all right, what was formed? Okay, well, I made this guy. That's some ethanol, and I made one of these. The coefficient here, we don't show it in the equation, but it's 1, and I have to be conscious of that. Okay, cool. That's all that was formed. Well, what was destroyed? We destroyed 1 mole of water, H2O liquid, and we destroyed 1 mole of C2H4. That's my friend ethylene. Okay, cool. So what I'm going to do is I'm going to say the delta H of the reaction is equal to the delta H of formation for everything formed minus the delta H of formation for everything that was destroyed. So this is what my delta H should look like, and I can just plug in these delta H's of formation from our real cool table. So it's going to look like this. I can just pull those numbers out of the table, and I can do some math, and I come up with negative 44.2 kilojoules per mole. So this tells me now that every time I want to carry out this reaction, for every 1 mole that is produced of product or react of these guys, it's going to produce 44.2 kilojoules. Neat. Let's look at another thing. Nice. Oh, what's this slide? We got a braided beard. And we got another braided beard. An old man with a beard. Can you see what I see? Zoom in. No, zoom in more. See that? What is that? What a face? Oh my god. Anyway. So here, let's try another problem. This one's a little bit spicier. So still, I want you to calculate the delta H of reaction using the delta H values of formation that are provided. So why don't you pause the video and see if you can give that a try. Neat. Well, let's talk about it together. First, I'm going to say, all right, what was formed? Well, we're going to make 2 moles of CO2. We're also going to make 2 moles of water. So we need to account for these coefficients that are in our balanced chemical equation. And then we need to say what was destroyed. Well, we're going to destroy 1 mole of ethylene, and we're going to destroy 1 mole, or not 1, that's a 3 moles of oxygen. So I'm going to need to take this into account when I'm calculating the delta H of the reaction. The delta H of the reaction should be equal to 2 times the delta H of formation for CO2, because I'm forming 2 moles of CO2 every time 1 mole of ethylene reacts. And I'm going to put in a 2 in front of my H2O as well. And I'll put a 3 in front of my O2. That's not going to matter, as it turns out. Remember, the delta H of formation for pure substances is going to be 0. So you may have said to yourself, well, how can I solve this if oxygen's delta H of formation isn't listed? Because oxygen is a pure element, just oxygen, in its natural state as a gas, the delta H of formation will be 0. But all these other dudes I can find on the table and plug in. Now it's just a matter of doing some math. I'll distribute these numbers into the fractions, or into the parentheses, and then I'll just add and subtract everything as needed to get my final answer of negative 1,322.9 kilojoules per mole. And this makes sense to me because this is a combustion reaction, and I know combustion reactions pretty much always release heat, are exothermic. So this seems good. Nice. Cool. Well, just some follow-up stuff. What way I've described doing this math, usually it's noted like this, using a sigma notation. So this sigma means add all these dudes up. And it's basically what we described. The delta H of reaction is equal to all the delta H's of formation added up. That's what the sigma says. It says, hey, add up all these guys, all the delta H's of formation for your products. And then we subtracted from that all the delta H's of formation for reactants. Sigma says, basically add all those dudes up and then you're going to subtract them out. So this is usually how you will see how to calculate delta H of reaction from delta H of formation. Hold on, let's get this finished. And so the last thing I will say is that usually a reaction will be balanced so that at least one chemical has a coefficient of 1. And if we're talking about a particular chemical or studying a particular chemical, we're going to want to set up our balanced equation so that that chemical has a coefficient of 1. For instance, if I were writing out this equation and I were thinking specifically about water, I would want to make sure that my coefficient of water was 1, so that when I do calculations, it's per kilojoules per mole of water. And even though that gives me a 1/2 coefficient in front of oxygen, that's okay in this situation because thermochemistry is some interesting stuff. Well, that's the end of this video. I hope you feel like you understand a little bit more about delta H of formation, delta H of reaction, how those two dudes relate, and how we can use delta HF to calculate delta H reaction. Sweet, ta-ta, have a great rest of your life.